In the Hohenberg-Kohn theorem, we saw that if we had this universal functional, then we can get easily the minimizing that with respect to the electronic density. We can get the ground state electronic density and the ground state energy. The thing is that getting that universal functional of the density, that's extremely difficult. There is no successful expression for that in terms of the density. So here we're going to see which was the strategy that Kohn-Sham followed in order to have a good expression for that universal functional, how they decompose that in different terms. So basically we're going to see the basics of this Kohn-Sham method. So basically, they divided that or decomposed that universal function in two different terms. One that was called TS, and we're going to define next. And the other one, which is going to be the rest, basically, is this one, and we're going to call it the Hartree exchange and correlation function. That was why it was called EHXC, which is also a functional of the density. So we're going to see which is this one, which is the first one, which is quite a tricky thing. So first, this one is the non-interacting kinetic energy functional. This is not the functional of the kinetic energy of the real system. No, this is basically what they did was the idea was to substitute the real system with a non-interacting system. Okay, we know that the non-interacting system, the wave function of the non-interacting system can be described by Slater determinants. And this one is going to be the kinetic energy functional of this non-interacting system. And how is defined that energy functional, that kinetic energy functional of that non-interactive system? That's defined in this way here. This is the way they defined the kinetic energy functional for that non-interacting system. So remember that for a non-interactive system, the wave function is somehow easier in the sense that it's Slater determinants. So basically, it's defined the following way. For a fixed density, for a fixed electronic density, you minimize the kinetic energy of that non-interactive system, so that here the wave function you have are different Slater determinants. So you minimize the kinetic energy for different Slater determinants that have that electronic density n. So if you minimizing that, you get that functional. Okay, therefore, the minimization of this one, of the kinetic energy of that non-interactive system, is done over these normalized single determinant wave functions, these are Slater determinants, which yield that fixed electronic density. Or we said in a different way, for a given electronic density, the minimizing single determinant wave function, which is this one, this is the wave function that minimizes that, is going to be called, we're going to call it the Kohn-Sham wave function. So remember that here, these are going to be Slater determinants that is going to describe that fictitious non-interactive system. And we're going to denote that Kohn-Sham wave function in this way. Of course, it's going to be a functional of the density, because for a fixed density, we minimize with respect to different Slater determinants that give that electronic density. So this is the way that Kohn-Sham defined that non-interacting kinetic energy functional. So the first term in this decomposition of this universal function. And the rest, in order to get the exact one, is going to be given by this Hartree exchange and correlation function that, of course, we don't know any accurate expression for that. But this is the strategy they follow. They separated in these two contributions that I want to insist that The first one is the non-interacting kinetic energy functional. The first one is not the kinetic energy functional of the real system. This is the kinetic energy functional of this fictitious non-interacting system. So once we have considered that decomposition here, then they have the following idea in this Kohn-Sham method. So the idea of the Kohn-Sham method is to use the exact expression of the non-interacting kinetic energy functional we have defined before by reformulating the variational property of that universal functional, but now we are going to do the variational procedure not in terms of the electronic density, but in terms of these single determinant wave functions that we have considered in order to define that kinetic energy functional. Okay, how it's done this one? Okay, first of all, remember that considering the variational property, the ground state energy of the system is just the minimum with respect to the electronic density of the total functional of the system, where it has like two different terms. First, this F, it's given like the universal functional of the electronic system, and then we have another term which is going to be related with the external potential here. Okay, now in the second step here, we are going to include the decomposition we have defined before, where considering that Kohn-Sham method, they split it or decomposed that universal functional in two different terms. One, it was Ts, and the other was, which was a function of the density, and the other was the Hartree exchange and correlation functional, which depends on the electronic density. Okay, the Ts, remember, that is this one. It was the kinetic energy functional of this non-interacting system. And then we have the rest, which is going to be the Hartree exchange and correlation energy. Okay. And then we have this term, again, which is related with the external potential. Now, the next step is going to be the following. So remember that the density associated to that Slater determinant that minimizes that functional, it's going to be this n density. So we can write that in the following way. As these Slater determinants are giving that electronic density, we can write in the following. That's the same as writing in this way, because these Slater determinants we have here are given that electronic density. So we can write this term in this way as well. So what we are going to do in the following is we are going to insert that term here. We are going to insert that term here in this sandwich here. And that's what we are doing here. So this first term, which includes the kinetic energy, and then we have the Vx, okay, and then we have the rest, which is going to be again the exchange, the Hartree exchange and correlation energy. So as you can see here, you can see everything here. This one is in terms of this Slater determinants. So of this is in terms of these non-interacting wave functions. And actually this density, which is like the variable that depends where depends this functional here, can be also written in terms of these Slater determinants, because these Slater determinants are giving that electronic density. So everything here can be written in terms of these wave functions of this fictitious non-interacting system. So therefore, instead of using this two-step procedure in order to get this minimization, which basically is the following. First, for a fixed density, we minimize with respect to the Slater determinants that are giving that electronic density, and then we are getting therefore these Kohn-Sham wave functions, and then you minimize with respect to the electronic density. Okay, instead of doing that, as any electronic density can be obtained in terms of the Slater determinants, and this we have this expression here, which is just a function of the Slater determinants. What we can do is just basically minimize with respect to the Slater determinants. So, as you can see here, the ground state can be written, therefore, according to that, as the minimization with respect to the Slater determinant of this non-interacting system, non-interacting fictitious system of this contribution here, which is given the kinetic energy of this non-interacting system plus the external external potential contribution plus the rest of the functional, which we call it Hartree exchange and correlation functional. And doing that minimization with respect to the wave function with this Slater determinant, we should get the same ground state energy. And considering the Kohn-Sham wave function that minimizes that, we should get the same ground state density as we could get in principle, considering this initial minimization here, where just the minimization were done in terms of the electronic density. The thing is that we cannot follow that because we don't know an accurate expression for this function. So following that idea, what we have now is the following. What we have now is that the ground state energy can be obtained considering the minimization of all these expressions here with respect to the external, with the Slater determinant of this fictitious non-interacting system. Thus, the exact ground state energy and density can be in principle be obtained by minimizing over single determinant, this is Slater determinant wave functions only. Okay, so that's in principle strange. So this is the strange. So what we are getting, because it seems that we are going back in the sense that what we had before, we had here that if we had the function of the density, of which was a simple function to deal with, getting that, we just needed to do the minimization with respect to the electronic density in order to have the ground state properties. Then, according to this new expression we are getting, is that now we are going back to, we have reintroduced a wave function here in order to do the minimization instead of using the electronic density. So even though a wave function has been reintroduced here, this wave function is the wave function of this fictitious system, of this non-interacting system. So again, it's a single determinant and represents a tremendous simplification on the usual variation theorem, where it involves a general wave function. So we are not considering the wave function here of a real system, where the expression of this wave function can be in general extremely complicated. Here we are just considering these Slater determinants. However, of course, the problem still is difficult because we don't know how we are going to get this wave function that minimizes that, but that's going to be for next, right? But the thing is true that the kind of wave functions we are using here are, of course, much easier than the wave functions of the real system, because these wave functions correspond again to this non-interacting system. They are going to be Slater determinants. And the advantage of this Kohn-Sham method is that a major part of this kinetic energy here can be, of course, the one associated to this non-interactive system, but they could be treated explicitly, and we'll see that, with these single determinant wave functions. and only, it's not little thing, but only in principle the rest, which is going to be this one, this exchange, the Hartree exchange and correlation term, needs to be approximated as a function of the density. The thing is that usually the kinetic energy it's usually the hardest part to have an approximation for the functional. So that's why this method resulted quite successful in order to get a practical version of the density functional theory. But first here what we have seen is the basics of this Kohn-Sham method, where again the basic idea was to substitute the real system with a non-interacting one and describe this ground state energy just in terms of minimization over that Slater determinant of this expression here. Of course, many things remains to be done here. How this minimization is done and what's the real expression or what's an approximated expression we can get for that Hartree exchange and correlation energy. So we're going to try to answer to these questions step by step in the following videos.